These didn't print out again. This is Math 2413, Thursday, day 17. Now we're going to start chapter 4. The extreme values of functions on closed intervals. What this chapter is talking about, chapter 4 deals with the applications of derivatives. What are they used for? Calculus is a big tool. For example, we look at how big is a cylinder should it be to hold X number of units of the volume of water? What is the width? What is the height of this cylinder? Yeah, so we have to look at X and H. In business, what profits, how many production units do we have to make in order for our profit to exceed this value here? Then that's marginal revenue, marginal cost, which is derivatives. So that's what we're going to look at here in this chapter. And again, I wish it would have printed because I have a whole bunch of these sheets for y'all. But what does it mean, extreme values? What's an extreme value? No, because limits aren't really extreme. They're just what we get to. Because for a limit, if I give a point here, as long as I have my closed interval, I can get to that point there. The limit is what value it approaches at C. That's not really an extreme value. Extreme values, let's say I had a graph here. This is from A, and this is to B. It's a closed interval. Here, we're going to stress the facts that f of x has to be a continuous function, which means there can't be any breaks. It has to be on a closed interval. And it has to be differentiable, which means that the limits have to exist at every point along the way between A and B. If any of those don't work, then a lot of stuff we're doing here may not work. You'll get an answer, but it may not be the valid answer. So with this one, how many extreme values do you see? Extreme means the highest or lowest. Well, we have one here, we have one there, we have one there, and we have one there. When we say extreme, we're looking at either the maximum or minimum. But now, is there one definition of maximum minimum? No, because what we can say is we can have a local extrema, which means on a smaller interval, or we can talk about a global or absolute extrema. That means over the entire thing. So in our picture here, let's call that A, we'll call that B, we'll call that C, and we'll call this one D. How many local extrema do we have? 4. Because each one of these I can make my own interval however size I want it. So each one of these are local extrema. Is this a max or a minima? It's a minimum. It's a local minimum because minimum means lowest, smallest. This one is a local maximum. This one, local minimum, and this one is a local max. So we have 4 local mins and maxes. Now, do we have an absolute or a global extrema? We have 2 of them. What's the highest point? D is the highest point. So D is our absolute maximum. You can only have one maxima or minima, absolute maxima, minima. And which one is our lowest point? A is our absolute minimum. Do we have to have an absolute maximum minima? Why not? No. I was going to say why not no matter what you said. Good point. A function can be a straight line. That's it. I didn't think about that. Wasn't where I was going, but you beat me there. In other words, can a graph look like this? No. Because I said, the first thing I said was we have to be in a closed interval. It cannot go to infinity. It has to be on a closed interval. Has to be continuous. Has to be differentiable on every point inside there. In other words, there can't be any jump discontinuities. So our functions can never have arrows go both ways. So yes, because even if we look like this, if we put dots here, and this is our A and this is our B, our interval, there are going to be extrema points in there. We have to look at 3 things, I'll say. We have to look at the endpoints. And we have to look at all extrema points called interior points. These are called exterior points. These are called interior points. How do we find extrema points inside an interval? What if we don't have the line? I just give you a function. What do you do with the function? How do you find this extrema or that extrema? Those are vertices. Yes, this is a vertex. It's a maximum. And this vertex is a minimum. But how do I find vertices? That's in algebra. We're in calculus now. But you're right. That's how we find, but that only works for quadratic equations. The beautiful thing about calculus is we have nth order differential equations. So how would we find the vertices? Yes. What about the tangents? What about the lines tangent to the curve at that point? What do they look like? They're horizontal. So what do we know about horizontal tangent lines? What do they have? They have what? The slope is 0. Now, how does that relate to derivatives? Exactly, because the derivative of f is the slope. We set those equal to 0 to solve for x, and that'll give us the x values of where our vertices exist. Oh, so that's how we find the x values. Plug the x values back in the function, and now we have a point, xy. You're right. So you see how all this stuff fits together now. The vertices have the slope equals 0. the slope is the first derivative. Find the first derivative, set the equation equals 0, solve for x, and all those x's are going to be our vertices. And then once you find the points of all of these, let's say our points for all in this graph here, for A was -5, -7. For this next one was -3, 4. This next point was at 2, -5. And this last one was at 6, 9. These are all 4 points. So we found the interior points. Take the first derivative, set it equals 0, solve for x, and then put them back to inside there, and you get the location. These are for the interior points. Then we take the endpoints, the A and the B. This one is the location of f of A. This one is the... So we have to not only find the interior points, but we also have to take the endpoints also. Let's now say these are all the points that we found. They're all local maxima or minima. Do we have an absolute maxima, absolute minima? Where's the absolute minima? Looking at these points. Minima. Well, look at the y values. This is the smallest y value. So that's the absolute min. What's the largest y value? That one. So this is the absolute max. And they're all local maximum minima. Let's look at some examples here. Oh, here's example 1. I mean, does this make sense? I'm trying to relate everything we've been doing so far to how it relates to what we're trying to get to. So the derivative finds a slope. The slope where it's 0 is a vertex. And then we also look at the endpoints. So now we have all those. So look at these graphs here. This is example 1. Absolute extrema of the following functions and their domains can be seen in this graph below. Find each function has the same defining equation, y equals x squared, but the domains vary. Here, the domain is negative infinity, positive infinity. So if it's negative infinity, positive infinity, what do we have? Do we have a maximum or a minimum? We have a minima. It's the lowest point. Is it a local or absolute? Both. But we say it's absolute minimum. It occurs at the vertex. Now we're looking at the positive side from 0 to 2. So now we're looking at specifically that domain. Do we have an absolute minima, absolute maximum? Yeah. The minimum's at 0, the maximum's at 2. From 0 to 2, where I cannot use 0. It's an open circle there. Do I have an absolute minimum? No. Because I can't get to it. I can't define what it is. You can't give me an x value that gives me the lowest point, because I could always subtract 1/1,000,000th, and you're always going to be smaller. So we can't get to it. So we're only going to have a maximum point. The point has to exist in order to be a maximum or minimum. We cannot have an open circle. Here, open circles at both ends. If it's open circle at both ends, we have no maximum or minima. We can see that something has to exist, but we can't get to it. Because any value you give me, I could increase it further. And now it just ruined your answer. Now, extreme value theorem. The extreme value theorem helps us define what we're talking about here. So we're going to write that down. The extreme value theorem says if f is continuous, okay, here, this is important. F is continuous on a closed interval if it's closed, that means it's bounded. Something has to exist there. Now, why is that important? Because can we use the endpoints? Yeah, it wasn't like the parentheses. So now we can determine the function attains both an absolute maximum and an absolute minimum in that domain somewhere. Unless, as you said, it's a constant function, it's a horizontal line. That would ruin it. If it's a horizontal line, it has nothing because we take a derivative of it, we get zero. So there's nothing. So that is, there are numbers x1 and x2 inside the function where f of x1 is a minimum, f of x2 is a maximum, where the minimum is less than the maximum. This is a very important concept because it tells us that inside any closed interval, a differentiable function will have high and low points. So, all right, you still writing? Here are some examples. Because it's essential. This is the notes I was going to give you guys. It's essential that the function is in a closed interval. The the domain is a finite domain, and the function is continuous. Those have to be true. So if that's true between A and B, do we have a maximum minimum? Yes. The highest and lowest points are here. Absolutes. How about this one? Inside A and B. Yes, this is the highest and this is the lowest. In this one, inside A and B. Here we have a maximum point. Here we have a minimum point. Because we stop at B. The graph itself can go on anywhere it wants to, but we're talking about a closed interval. So you see, how do we find these points? Set the derivative equals 0, and that'll give us the x value. Plug it into the function, it'll give us the y value. It'll give us the location. But all we're looking for is on the y-axis. What's the highest and lowest points? And we relate to the x value. So this is the lowest point, happens at x1. The highest point happens at b. So you see, you have to try all the interior points as well as the endpoints. Finding extrema. Theorem 2. The first derivative theorem for local extrema states this. If x has a local maximum minimum value at an interior point C on its domain, and f is defined at C, then the derivative of f at that point C equals 0. Now, what does all that stuff mean? F is continuous. It's differentiable. It's on a closed interval. Here's our point C. If I took the derivative and set that equal to 0, the slope is 0 at that point. That means it's a maxima or a minimum. That's what that theorem tells us. It's what we've just been talking about. So what this theorem says is if we take the derivative, set it equals 0, whatever x value that makes it equal 0 is the location, is the x value of our maximum or minimum. Do we know if it's maximum or minima? Not until we check everything else. That's why you have to check the endpoints. You have to check the endpoints because your graph this is A, and this is B, and this is C. At C, my first derivative is equal to 0 at C. Now, how do we know if that's a local maximum or minimum? On a graph, it's easy. But if we didn't have a graph, we'd also have to look at the endpoints. If this y value is lower than those two, it's a minimum. In this one, this is our maxima, this is our minima, highest and lowest. What's a relative maxima and minima? What's a relative extrema? Relative maxima and minima or extrema are the locations of these points and any other C inside there. These are the endpoints. You always have to try those because it's a finite domain. And yeah, they're going to be relative on their little small domain. If A is here and B is here, here are our extrema points. Is A maxima or minima? Absolute? No, because this one's lower, this one's higher. But it is a relative extrema. The endpoints, by definition, are relative extrema because that's where they stop. These interior points are also relative extrema because they happen in some smaller interval. So that's what relative means. It's relative to whatever small interval you create. Absolute is over the entire picture. Oh, let's look at this. An interior point of a domain of a function f where f of f prime is 0 is called a critical point of f. These points here inside the interior points. Let's call that x1, x2, x3. These are called critical points. So we have to give a name to all the x values where the derivative is equal to 0. So the critical points, x values where the f prime at those CPs is 0. They're the vertices. Now, why they call critical points is because we know that if we had a graph like this, it's part of another one. The derivative here is 0. Now, without looking at a graph, how can we determine if that's a maximum or a minimum? If f of x1 is a max, or relative max, then what has to be true? That means everything to the left of it, all of the x values, or even the derivative, they have to be positive. So all the x values to the left of it, their slope is positive, which means it's increasing. All the x values after it are going to be negative. So if we look at all of these points to the left of it and we put them in the first derivative, what do we know the answer is going to be? Greater than zero, because they're all going to be positive. If we put all the x values to the right side of x1 inside the first derivative, all of those are going to be negative, which means that they're going down. At f of x1, if we put in the first derivative, what's it going to equal? Zero. Think of a roller coaster. If you're climbing, you feel yourself push back in the chair. You get to the very top, what happens? You're just sitting down. Then the other side, what happens? You're now flying. So either way, it's beginning and being pushed back to your seat going up, and when you're going down, you're also being pushed back. Up here, nothing. But you know something's going to happen on a roller coaster. That's the best feeling in the world, especially if you're in the front. You can see it. All right, so look at example 2. It says, find the absolute maxima and minima of f of x equals x squared on the interval -2, 1. Find the absolute maximum minima. Next one. So what do you have to do? Without drawing a graph, I don't want you to draw a graph. No graphs. Because what we're looking for are looking at the values of the points. So the first thing we have to do is take the derivative, which is what? Do what with that? Set that equal to 0 and solve for x. So we have 2x equals 0, x equals 0. So what does this tell us? We have an extreme value at x equals 0. So if we put it in the original function, so we have an extreme value at 0, 0. Is it a maxima or a minima? Well, so we know at 0, we have a maximum or minimum. We have to try the endpoints also. So if we look at a point on this side and plug it in the first derivative, let's try -1. The first derivative was 2x. So 2 times -1 equals -2. What does that tell me about the slope? Is it increasing or decreasing? It's decreasing. So here on this side, the slope is going down. That's the m is negative. Let's try this side. The first derivative when x is 1. 2 times 1 is 2. It's positive, so it's increasing. The slope is bigger than 0. So we know this has to be at 0. It has to be a minimum. It has to be the absolute minimum. Why? If we plug in the values of our endpoints, we have to try the endpoints, and we have to try where the critical point is. This value we don't really have to do anything about. It's not going to help us any because it's not the endpoint and it's not a critical point. So this is our CP. At -2, we got a 4. At 0, we got a 0. At 1, we get a 1. So looking at these values, which one is the biggest? So we have an absolute maximum at x equals -2. We have an absolute minimum at x equals 0. So that's how we look at the stuff. So far, so good. So this is what it's telling us. This next one you're not going to like too much, but example 3. Find the absolute max and min. He says find the absolute minimum of f of x equals 10x times 2 minus ln x on the interval 1 e squared. So we have, for example, 4. So that's our function. We have our interval here. Yeah, no, it doesn't look too fun, does it? Because we also now we we have to do we have to try the x values at the endpoints. And we also have to try it at all the critical points. Which find all so how do we find the critical points? Take the derivative of the function. So this we have to use the product rule, f and g. So f is 10x, g is 2 minus ln x. Now we have to find the derivatives. So the derivative of 10x is 10. Derivative of 2 minus ln x. Derivative of 2 is negative. Derivative of ln x. Very good. 1 over x. So it's negative 1 over x. Since it's a product rule, we add. So this becomes 10 times 2 ln x plus 10x negative 1 over x, which makes it, let's make it 20 minus 10 ln x minus 10. Because the x's cancel. 10 minus 20 minus 10 is 10 minus 10 ln x. We can factor out a 10. Set those equal to 0. So 1 minus ln x equals 0. So where does ln x equal 1? So ln x equals 1. Remember, this is log base e of x equals 1. So x is equal to e to the first power. So our critical point is at e. Remember the conversion from logarithmic to exponentials? So there's a logarithmic. The base pushes up the answer. The log drops off, and you have the x. This is the conversion between exponentials and logarithmic. And ln is simply log base e. So we only have one critical point at e. We have to try all three of these, and that'll tell us whether we have a maximum, minima, or what. So let's try these. 1 e squared and e. So it's 10 times 1, 2 minus ln 1, 10 times e squared, 2 minus ln e squared, 10 times e, 2 minus ln e. ln1 is what? Log base anything of 1 is 0. Because the only way that can be true is anything to the power 0 is 1. So that is 0. So 10 times 2 is 20. So we have 10 e squared. ln e squared has an exponent, so it goes out in front. ln e, log base e of e, is 1 because of this rule. Log base a of a is 1. This is log base e of e is 1. That's what that says. So we have, this becomes 2. 2 minus 2 is 0. That becomes 2. 2 minus 2 is 0. So that's 0. 10e, ln e is 1. So this becomes 10e. E is a constant, 2.718175, whatever. Oh, what it was. Times 10, it becomes 27. So do we have an absolute maxima, absolute minima? The biggest y value is 27. So it's at E 27. And the absolute minima is 0. So it's at E squared at 0. So if we were to look at the graph of this thing, 1, it equals 20. At E squared, or E equals 27. And at E squared equals 0. So our graph looks something like this. Our maximum is here, our minimum is here. One more. Example 4. Again, find the maximum minima of this function on the interval -2, 3. Does anybody have a class next? Because we're almost, I mean, so this is our last example, then we're done. So the derivative is going to be 2/3 x to the power -1/3, which makes it 2/3 cube root of x. Can we set that equal to 0? Okay, it's a fraction. What's the only way a fraction can equal 0? If the top is 0. Because if we set this thing equal to 0, and multiply both sides by the denominator, it becomes 0. So there are no critical points. Because if we multiply both sides by 3 cube root of x, those cancel, and that becomes 0. So we can't set it equal to 0. Remember, if you have fractions, the only way it can be 0 is if the top equals 0. But we also know x cannot equal 0. Anyway, so let's look at this. Because at 0, it's going to be a weird point. Well, we'll look at 0 also. At -2, what do we get? So -2, if we square it and then cube root it, we get cube root of 4. So the cube root of 9. That's a little bit bigger than 2. Because cube root of 8 is what? One. The cube root of 8 is 2. Cube root of 9 is just a little bit bigger. So something like 2 point something. So this is 2 point, let's say 1. At 0, we get 0 in here. So out of these, what's our highest point? What's our lowest point? So this one is cube root of 4. This one's 2.1. 2.1 is the maximum. So this is our absolute max. What's our minimum? At 0. So this is our absolute minimum. What the graph looks like is this. What the graph f of x equals x. This is the same thing as x to the power of 1/3 squared. Or cube root of x squared. What does the cube root of x look like? Remember, square root of x is this graph. Cube root can be positive and it can be negative, right? That's the cube root of x. So far, so good. If we square it, what happens? The negatives become positive. So it will look like that. And our domain was from where to where? -2 to 3. Yeah. So our minimum point, our absolute min is at 0, and the max is at 3. Yeah, the hardest part of these things is by just doing the derivatives. Make sense? That confuse your brains? These are now in chapter 4, all we're gonna do is applications. And this is the beginning part, this is how we check to see what our highest and lowest points are, because all of it has to stay within that domain. All right, we'll end it there today. I will give you next Wednesday off because our next Tuesday off. Yes. You don't have to see my face Tuesday. It's going to be online. Yeah, because my presentation is until 1:45 or 1:50. So